Yeah, I don't think that.
Yeah.
Done.
Yeah. Yeah. I didn't make.
Talking about next semester?
Yeah. Yeah, I was waiting to think out.
Yeah, it's Xiao Yu, and it's a complicated one.
Yeah, mine will be.
Yeah, I just had, I need the 8 AM one.
Yeah.
I grew up first. What? Oh my god. That's so bad. No, that's not. That is actually terrible. Yeah, and I'm computer science.
Oh, that's 60/70.
Yeah, but I wanted to take it next semester, but it was already full, so I couldn't do it.
Right now, so.
That was also full too.
Looking at it. It's alright. Yeah, yeah.
I mean, it'll be fine though.
Yeah.
It's,
Yeah, sorry, man, I don't know. Alright.
I also have like theory of computation, but it's like it's like 4 p.m. to like 5:15 p.m. It's like, and there's like this big gap in my schedule for my class, like it's like at like 12:20 or something, and then 4 hours, my class begins at 4.
Yeah. You didn't know what we saw. With it. Wednesday, yeah. And I'm hiking the class. Yeah. Yeah. Do that. Yeah, I don't know, and no. That's the right now, but. With my schedule. I'm gonna go away for. I thought that I missed it, and then I was like, I got that.
Hey, I have 9:30, so we can get started, and we're going to just be doing review for this today and then the next 3 lectures, and then the week after is your presentations. And my plan is I'll review kind of like what we did for the other 2 exams this lecture and Monday. And then on Wednesday and Friday of next week, I'll go over the homework that is due on Monday. And for our review, we kind of have like the second half of chapter 4 as well as chapter 5. Chapter 4, we covered more pipelining techniques, since exam 2. And chapter 5 is our caching and memory hierarchy. So this is the first section I want us to look at. So it's going to be about this data path. So this is one of our pipeline data paths. And the question is, what is a penalty for a branch manipulation? And we want to see a multi-cycle pipeline diagram of an example of how this would work if we mispredict and have that penalty. So I'm gonna go back to the diagram and think about this. And I think we can just talk to each other if you have people around you that you want to discuss with about this question. But you should be able to see from the data path, where is the branch resolved? How many other instructions are going to be fetched that need to be removed from the pipeline because they were fetched incorrectly? I have an answer for this. Where you step. So. Anyone still thinking about this? Okay, so. Let's look at the data path here. So our branch instruction. What happens during the branch instruction? Without looking at the data path, what do we need to do for the branch instruction?
Calculate the new PC that we're jumping to.
As well as? What do we do with the sign extent? Well, that is for calculating the PC. But what else do we do though?
rewrite the PC.
After that, if we do branch, yes, but how do we know if we're gonna branch or not?
Compare the registers.
We compare the registers. So our job here is where are we comparing the registers? So for our branch instruction, in the fetch stage, we just fetch the instruction. And then over here, in the decode stage, we're just extracting the sign extended immediate. And we're reading the two registers that we're going to compare to each other, right? And then in the next cycle, in here, we're going to use the ALU to subtract the two registers from each other. And the zero flag will tell us if they're the same, right? Because if they subtract and the result is 0, then the 0 flag would be 1, saying that they're the same. And then over here, we have the sign extended immediate and then shifted right. I mean shift left by 2. And then we have the PC plus 4. We add, this is our target address, right? So it's here that we really resolve the branch, right? This is where when we know that we need to branch. And in the next cycle, we have that we are a branch instruction. The 0 flag was 1. And we also have the new PC. All of this, these two paths, it tells us that we need to update the PC to this new target address. Okay. So we figure it out in the execute stage, but we don't really change the PC until the memory stage. So we can draw out a little diagram to help us with this. So let's say this is a branch. Our branch will be Q. So instruction set is the first thing that we do. Then we do instruction decode. And let's call this int1. And when we decode, we fetch based on our predictor, the taken or not taken. But we're trying to see what is the mispredict. So let's say that we're supposed to be taking this branch, but we don't take the branch. Like our predictor says we don't take it. So we're fetching the instruction right after the branch. And then here is where we execute, right? And instruction 2. This one gets to decode. This one gets fetched. Instruction 3. This is where we figure out that we have a problem, right? Because we know that we are going to branch now. And in now this memory stage, well, this one is in executes. And this one is in decode. We're going to update the PC to be the correct one to fetch. And now when we're in write back, this becomes no op, and I forgot to put the fetch here. This is no op, and here instruction 1, but the correct one now, because this is where after we've changed the PC, we can now fetch. So these will finish off. There are no ops, no op. This can do decode. We can fetch the next instruction. So here I have basically thrown out 3 instructions. My penalty is 3 cycles. Right? So this is what you would use to show. And we knew this is how it would run because we saw that we don't even calculate the target address until executes, and we don't know if we're going to branch until executes, and then we update the branch. Well, with the branch, we update PC in the memory stage, right? And we're fine to flush all of these instructions out because the furthest it got to was execute, so it hasn't modified any of our registers or memory, right? So if we just zero them all out, turn them into no ops, then it's like they never executed. Okay. Is this clear to you guys? All right. So you should be able to look at the data path and answer questions like this. This is something that could be asked of you on the exam. Okay. And also in your homework, you have something similar to this, where it asks you to make the multi-cycle pipeline diagram for a branch mispredict, right? But the penalty there is only one cycle. Because what we went over in class is that we actually moved all of this into the decode stage. Right? But that's a different data path. So you just need to be able to identify and follow the data path. Okay? All right. So the next question, and again, you can talk to people around you. You don't need to do this all on your own. Start with. So given the branch pattern below, fill in the predictions for a 1-bit predictor and a 2-bit predictor. And we want to assume that the 1-bit initializes to taken and the 2-bit initializes to weakly taken. So we're going to have 2 more patterns here. So we have 1-bit and 2-bit. Are you guys still thinking about this? Are you done with thinking about this? Okay. So we can go over this together. And I think we can kind of work through this as a class. If someone can tell me for the 1 bit, what is my first prediction? Yep. And do I need to update my predictor? My second prediction? And do I need to update my predictor? And then third prediction? Fourth prediction? So 1, 2, 3, 4, 5. Fifth prediction? Taken. Do I need to update my predictor? No. Yet, right? And then my next prediction is? Taken. Now do I need to update my predictor?
Yes.
Yeah.
Yes. Because it should have been not taken. So I only have 1 bit, so now what am I predicting? Do I need to update my predictor?
No.
And then my next prediction?
Not taken.
And then we're done. Right? So what about the 2-bit predictor? What's my first prediction? Do I need to update my predictor?
Yes.
Yes. So what does it become now?
Strongly taken.
Yes. My next prediction?
Taken.
And do I need to update the predictor?
No.
No.
Next prediction?
Taken.
Taken.
Update predictor or no?
No.
And next prediction?
Taken.
Taken.
Update predictor?
No.
No.
Next prediction?
Taken.
Taken.
Update predictor?
No.
So next prediction is?
Taken.
Do I need to update the predictor?
Yes, weekly
Yeah.
taken.
Okay. So my next prediction?
Taken.
And do I need to update the predictor?
Yes, weekly not taken.
And now my next prediction?
Not taken.
And my predictor is now updated to? Yes. So it seems that you guys have this one down, right? Okay, so the next question, this is going to be the longest question. This one will help you with your homework as well. And on the exam, this kind of question will for sure show up. So you do need to know how to do this. It will be one of your 2 questions. And I will encourage you to talk to the other people around you to answer this question. you are stuck, it will be helpful to talk through it with someone else around.
So how would what is the easy guide and increase the plan penalties?
Oh, I didn't even realize that.
So
It's really gonna be fun. That's like 100 of equations for it.
well, not really, it's just- there's just a lot of solutions. So for so we think we might be able to use the BCPI and then like maybe figure out. This is. I think this is lecture. Yeah, I think it's 32, 33 or something.
It was 33.
Yeah, we're just trying to figure out what the CPI is. I was considering using BCPI equals PCPI plus PSPI plus PS. So, what is point?
I think that the CPI would be the base CPI plus the memory CPI. The base CPI plus.
So how do where's the best CPI though?
Like on the same side.
Yeah.
They're right next to each other.
I know, I mean, like, how do we get the MCPI for this equation, for this question?
It says it would be to
Oh, what was that?
access to her weapon and the misbreak after this stuff.
Do you have anything?
Oh, yeah, I can't use it from the CPI, but the CPI plus the CPI.
Do we know what do we know what each variable is, though? That's my concern.
You have the miss penalty on this, right?
And this,
Okay, I think let's go over this together. Because it seems like we should go over this again to make sure that you guys know how to do it. I'm gonna be flipping through the slides so I can get the information that I need, but I just want to first start with how do we get started with this question? So to do this question, usually what will be helpful, just like how it's broken down in the homework, is to break it down into different parts. So our CPI, our overall CPI is going to be, so we have the base CPI, so it's base CPI. And in this case, we're saying the base CPI includes the instructions and also handling data hazards. So it's going to be base CPI plus, and then We're also told information about branching. We have branch CPI. And we're also told information about our memory. So we have memory CPI as well. So let's first just calculate what is branch CPI. And then we'll calculate what is the memory CPI. And then we'll get the overall CPI, okay? So what is the CPI increase for branch penalties? So I just want to start with first, what is CPI? It's cycles per instruction. So CPI is clock cycles over instruction count, right? Right.
Yeah.
Alright, so we can break this down into, for all of my instructions, approximate, if everything is perfect, I never have any stalls, what is their approximate number of cycles for a pipeline design? So like running the whole program.
Sorry, what's the question again?
Let's think about it more simply. So if we have 5 instructions, how many cycles does it take to finish? 8, 5, not quite. 9, right? So it's the number of instructions plus 4, because that's how many we need to like flush out at the end, right? So if our instruction count is say 10 billion, then how many cycles does it take?
10 billion.
But can we just ignore the plus 4? So here, the cycle count for our instructions, if everything goes perfectly, is just instruction count, right? And then now we need to add on our other things, like if we have data hazard stalls or stall cycles, or if we have branch stall cycles, or if we have memory stall cycles, right? These are the 3 things that we covered. I don't hear any yes, no? Okay. And then that's all over instruction count, right? This gives us our total CPI. So we can also write this down as, this is instruction count over instruction count plus data hazard stall cycles over instruction count plus branch stall cycles over instruction count plus memory stall cycles over instruction count, right? This is the same thing. So this is where we get base CPI, right? This is our data CPI. This is our branch CPI. This is our memory CPI. Okay? Is this good for you guys? So now all we have to do first is calculate how many stall cycles we have, and then just divide that by instruction count, and that gives us our CPI increase for these different things. Okay? So for our branch penalties, what is our branch stall cycle count? Well, we have how many? We have a program where 10% of instructions are branch. So first, we have all of our instructions, so instruction count, and then times 10% are branches, right? And then of those 10% that are branches, we mispredict 3% of them, right? Yeah. So this gives us the number of branches where we have to serve the penalty, right? So if we multiply now by what that penalty is, which is 1, that gives us the total number of stalls per branches. Right? Because we calculated how many times we need to stall times how many cycles do we need to stall each one of those times, right? So what is this? Can someone tell me? Or actually, this instruction count 0.003, right? Okay. And now to get the branch CPI. Oh. Ignore that. So branch CPI is just the branch stall cycles divided by instruction count, right? So the branch CPI is just this. So this right here is equal to this. And we just calculated the top part. So we just need to divide by instruction count. Right? That's what we got down here. Stall cycle with instruction count times this. So if we divide by instruction count cancels. All right, so we can do the same thing now for our memory. The first thing is, what is our memory stall cycle? First, we have instruction count. And then we have what percent of instructions are memory?
5.
And then what percent of instructions are missing in L1? And now, what percent of instructions are hitting in L2? Sorry? Yes, 99.8. Right? Do you agree?
Yes.
Yeah. And then what is my penalty for accessing L2? Yes, 20 cycles. And now I also have the penalty of accessing the main memory. So I have instruction count again, right? And 5% of instructions are memory instructions. And 0.01% of them miss in L1. Yes.
Should that 20 be a 50?
Yeah, I think it was a 50. Yeah, it's 50. I don't know why I heard 20, but all right, so 50. And then 5% are memory instructions, 1% miss from L1. And what percent of those then also miss in L2? Right? 0.2%, right? And then our penalty is what? 200, right? So this gives me my number of stall cycles. right? So what is this? I don't know what this is. First, this one. Anyone tell me?
$0.02495.
0.2495. This is what you're saying?
Yeah.
Alright, and then what's the second one?
0.0002.
00. 2 zeros or 3 zeros?
There's 3 zeros.
Like this,
Yeah.
alright? And then if I add them, what do I get? Let's just call it this. Right, it's approximately this. And then line M CPI. What is that? Right? So then my CPI is 1.1 plus 0. What was the other one? 0.003 and plus 0.025. What is this? What? I don't have my calculator.
1.128.
So that's our CPI. Agreed? Yes. Okay, so now the next question is, what is the speed up of the processor if the branch predictor was perfect and the cache was perfect? So what does that mean? What is this CPI? If these things are perfect.
That would make your base CPI at 0, right?
You mean the branch CPI?
Yeah.
Yeah. So we have 1.1, so plus 0, and then what is our MCPI?
That also be 0.
Yes. So it's just whatever the base CPI is, right? Because there's no stall increase. And then what is our performance equation?
ET old over ET now.
Well, I'm asking just the performance equation, not BWF.
CPI
Huh?
times BC. Or no, CP
Uh-huh.
times IC.
Yes. So then our speed up is ET, so speed up is ET old over ET new, right? So ET old is the 1.128, right? That's our CPI. What's our cycle time? Do we know it? Know it? No. What's our instruction count?
Also,
What's our new CPI? What's our cycle time?
unknown.
Did we change it at all?
No.
Like the same? What's our instruction count?
Also the same.
What's our speed up?
.0254.
So that means that our branch predictor and our caches are working very well, right? Because even if they were perfect, we hardly get any speed up. So this question is very similar to one of the questions on your homework, but be careful because this is not the same. Be careful on the last part, okay? And also, you don't have to deal with the two levels of cache. So for your question on your homework, if you miss from L1 cache, you don't also have to know if you hit in L2. You're just going to go to memory. You don't have this part. So this is one of the important things to understand. Like, where do we get how does CPI equal to all of these things with the base CPI? And how can we calculate the different CPIs individually by using these equations? And it's the same for, like, this process is the same for all of these different things. It's calculate the number of solves, divide by instruction count, that gives you the CPI increase. Right, so if we had information on how to calculate the data hazards, then we would also be able to do that, right? Yes. Yeah. Okay. So just so that's all we have for this. Or the reminder for you guys is that you have homework 5 due this coming Monday, which is May 1st, and then homework 6 is due the next Monday. And homework 6 is a little bit shorter. It's just calculating the CPI increase for multi-level cache. Yeah.
Is that our last homework?
Homework 6 is the last homework. I will release a study guide. Study guide will be due just right before the exam. Because basically, if you turn it in before the exam, that means that it was useful to you. So the poll everywhere for today, just answer anything, is 260. 260. 260.
Regarding our